Hello and welcome to OntologyTalk. I'm Adam Pease, and this is the third part of a series on graph representations. In the second part of this series, I started with some examples to walk you through basic ways of constructing graphs. A simple way that you might start with is representing relations or representing verbs as relations. So if you have the sentence Brutus stabbed Caesar, you'd have a node for Brutus, Caesar, and stabbed. But that quickly gets you into problems when you want to start saying more things about this event. And so the standard way of solving this problem in a graph is to do what's generally known as reification. So you're naming or creating a relationship. And so in this graph we call it a stabbing. And linguists also talk about this as so-called Davidsonian semantics. There's a philosopher in the philosophy of language, Donald Davidson, that wrote a very important paper on this topic back in the late 60s. So that's another name for taking this event and reifying it, so naming it and using that as a sort of hub and spokes relationship where we have the stabbing at the center and then a bunch of relations around it. And this works pretty well. But there is still some challenges, also that I mentioned in part 2. What if we want to say the opposite? We want to say there wasn't an event of this type with these relations. How do we handle that? And if we create this sort of not stabbing, does it apply to all the relationships? So we say that this event and all of its relationships do not hold, they're not true. That's certainly one way of interpreting this. But if we want to say something maybe a bit more specific, so Brutus didn't stab Caesar with a knife on Tuesday, he used a sword instead, so we want to say that it wasn't the case that the instrument used in the stabbing was a knife, then maybe we want to create the opposite of every relationship we have and prefix a not on it, so we'd have not instrument, not victim, not time, not agent, and so on. That's one way of doing it. But still, then there's more things that you might want to be able to say. What if you want the standard kind of logical relationships that you'd have in a programming language? So if we want to say that the instrument was either a knife or a sword, then we're probably going to need something like an OR node that's going to have two relationships to it, so two nodes that are related, a knife or a sword, have the relationship of instrument to the stabbing. And we'd expect this if we're programmers, so if we want to say something like this in Java, it's pretty natural. So we have an instance of an object, a stabbing object, we will call it stabbing1. It has a member variable of agent, and the value of that agent is Brutus. And it's also true that the value of the instrument member variable is either knife1 or sword1. So that'd be one way to talk about this in Java. There are also declarative languages. So Java is primarily a procedural language. It says what the computer should do. In Prolog, at least to an extent, its language is oriented to declarative statements. It says what is true, and it's up to an interpreter to run through the Prolog code and solve a problem, answer a query, respond to a request from the user using the facts that you've told it. Prolog, of course, does have the cut and the fail, which are some procedural hacks, but for now, let's look at Prolog as though it was purely declarative. So here's just, I've included some notes on here if you're unfamiliar with Prolog syntax. The comma means and, the semicolon means or, and so we have something that's roughly equivalent to what we were starting to say in Java on the previous slide. So if something is true, that's the sort of the result, which is stated backwards in Prolog compared to Java or Python or most other procedural languages. So if we have the agent of stabbing1 is Brutus, and we have either that the stabbing was done with a knife or a sword, then something about Brutus follows. That's how we'd read this in Prolog. So if we want to have and or, then we can sort of continue on in this vein in graphs, and what we wind up with is something that starts looking like an abstract syntax tree. Right? It's a way of representing syntax in a visual form, but it really is just syntax. Right? So here's what we'd have. We'd have that the agent of stabbing1 is Brutus, and it's true that, sort of within parentheses now, it's either true that the stabbing was done with a knife or the stabbing was done with a sword. And here I've kind of combined the two, right? I've got these predicates here as nodes, and what we really mean is something like this, where we have this relationship between Brutus and the stabbing and the knife. I should have made that a stabbing and a sword instead of a knife here down the second one, so sorry for the confusion. But then we also have the question of how do we represent the fact that we've got this stabbing in multiple places? We really want to be able to say that it's actually the same stabbing, but the other relationships that hold about the stabbing don't get combined in this same way, right? The fact that the stabbing above is related to Brutus and it's in this and relationship, it's different when it's sort of there's a relationship subject to an or. We've got to kind of keep these things separate, but then they're also related, and getting the semantics of that right, the meaning of that right, is certainly a bit challenging. So another way of handling this to make it clearer is to have what's known as named graphs or named subgraphs. Again, we're reifying the relationship, so we have stabbing relation 1, stabbing relation 2, stabbing relation 3, and then we can have a cleaner differentiation between the logical operations which hold between these whole subgraphs and the relations that hold between the participants in things like the instrument or the agent relationship. So the and applies to all of stabbing relation 1, and stabbing relation 1 is the relationship of Brutus being the agent of the stabbing. All right, that starts being a bit clearer, but the graph's getting pretty ugly pretty fast. And what happens if we want to talk about the if-then rules? So we've declared here the precondition of the rules. If Brutus is the agent of a stabbing and the stabbing was done with a knife or a sword, then something else follows. We haven't talked about the post-condition yet, but this is roughly what it might start to look like as a graph relation. Again, now it's just getting even more complicated. And what have we really accomplished? Well, essentially it's still an abstract syntax tree, right? And so the point of showing you this progression of examples is to lead you through the understanding of, the graphs can look very beautiful and elegant if we don't have logical operators, if we don't have conditionals, if we don't have the other features of logic like quantification, which I've talked about in some of my other videos, if we don't have negation, all these things that we as programmers we'd expect to have in any normal procedural language. It's kind of hard to push those things into a graph structure. If we do push them into the graph structure, they're going to wind up being an abstract syntax tree. And then in addition to the representation as an abstract syntax tree, we also need to actually encode the rules of logic in whatever inference procedure we're going to use to run over the graph and create new conclusions or test whether the graph is well formed. So the point to this is, why not just start with logic? The mathematics of first order logic, otherwise known as predicate calculus, has been around for about 100 years. So what I see in a lot of graph representations is that people get very attracted to the simplicity of the graph representation and the beauty of it, because you can have these lovely two-dimensional pictures of what looks like the knowledge of the graph, but as soon as you get into a little more complexity in terms of the knowledge that you're trying to represent, as soon as you have the notion of an OR node or a conditional, then a lot of that, or of higher arity relations, something like between that we covered in the first part of this series. As soon as you get that, things become more complicated, less attractive, and you actually haven't done anything special, right? You haven't done anything special that can't be done much better with just expressing things in logic, because you're either going to wind up with a graph that, although it's a graph, it looks very ugly and it's not as understandable visually, or you're going to leave out a lot of knowledge about the world that you just can't express in your sort of basic node and arc diagram. So I hope this, by going step by step, has piqued your interest and maybe raised some of these questions in your mind that you want to dig deeper and discover for yourself, and really understand whether your current system requirements are such that you should use a graph, or if you should go to something that's more conventional in the expressive logic space, like at least first order logic. Thanks for watching this latest edition of Ontology Talk. Please like, subscribe, and share if you found this interesting, and take a look at ontologyportal.org, where there's a lot more information.